Every narrative begins with a shift in perspective. We've stared at the sun for centuries, tracking sunspots, capturing flares, and marveling at coronal loops. But always from the same vantage point. We thought we saw the whole star. Until March 2025. That's when we first glimpsed its hidden face. Today on infinitMIND, we're going to witness a moment of cosmic revelation. The sun's south pole, finally unveiled by ESA and NASA's solar orbiter. And what we saw there during solar maximum isn't just beautiful, it's deeply unsettling. Set your expectations. This is going to alter everything we thought we knew about our star. It was a journey years in the making. Since its launch in 2020, Solar Orbiter has been slowly climbing out of the solar system's orbital plane, using gravity assists from Venus to tilt its orbit. In March 2025, it reached a critical milestone, 17 degrees out of the ecliptic, just high enough to peer over the sun's horizon and capture an image that no human or machine had ever seen. The south pole of our star. And what appeared wasn't the orderly, geometric magnetic structure many had imagined. It was chaos. The images returned to Earth showed a swirling sea of magnetic polarity, violent reds and blues, tangled and pulsating. Scientists were stunned. Instead of a simple magnetic reversal zone, they saw a battlefield of competing forces, locked in a dance of constant upheaval. But this was far more than a scientific curiosity. The sun's poles are not cosmetic features. They are the engine room of its magnetic field. It is here, in these hidden regions, that the sun's magnetic identity flips, resets, and recharges. And it is this magnetic activity that drives the phenomena we experience as space weather. Solar flares, coronal mass ejections, and the fast solar wind that shapes our entire heliosphere. And now, for the first time, we were watching that process in action. The instruments aboard Solar Orbiter painted a complete picture. PHI, the polarimetric and helioseismic imager, revealed the patchwork of chaotic magnetic domains. EUI, the extreme ultraviolet imager, captured towering plasma arcs and plumes, glowing at over 1,000,000 degrees. And SPICE, the spectral imaging of the coronal environment, traced fast-moving jets of carbon ions streaming out from the pole, likely the seeds of the solar wind itself. For decades, scientists have wondered why the sun's outer atmosphere, the corona, is so inexplicably hot, reaching temperatures hundreds of times greater than the solar surface. One leading theory is magnetic reconnection, field lines snapping and reforming, releasing bursts of energy. Now, with Solar Orbiter's polar data, we may be witnessing these reconnection events up close, where they seem to be happening with extraordinary frequency. But beyond the scientific marvel lies a deeper, more urgent question. What does this mean for us here on Earth? Because when the sun's magnetic field flips, as it is doing now, its entire behavior changes. The number of solar flares and coronal mass ejections increases dramatically. Some of these storms travel across the solar system, and when they strike Earth, they can wreak havoc on modern technology. History has shown us how vulnerable we are. The Carrington event of 1859 caused telegraph systems to spark and fail. In 1989, a solar storm knocked out Quebec's power grid, leaving millions in the dark. Today, a storm of similar magnitude could cripple satellites, disrupt GPS and communications networks, and even damage power infrastructure on a global scale. And this is where Solar Orbiter's mission becomes more than a scientific triumph. In 2022, the spacecraft provided an early warning of a CME, narrowing forecast windows from hours to minutes. It gave us a glimpse of a future where we can predict space weather, not just react to it. And that future depends on understanding the poles, because the poles are where the sun's magnetic identity is reborn. Over the next 4 years, Solar Orbiter will climb even higher to 33 degrees inclination, giving us an unprecedented view of the poles during the entire magnetic reversal process. We will see in real time how new magnetic structures emerge, migrate, and finally flip the sun's polarity. And the questions we face are profound. Will the two poles flip in perfect synchrony, or will one lag behind? Could asymmetry in this process trigger unexpected storms or influence the strength of future solar cycles? The answers could reshape our models of the sun and our ability to anticipate its moods. Yet the implications extend beyond academic interest. Every spacecraft, every astronaut, every airline passenger flying near the poles depends on accurate space weather forecasting. The ability to predict when and where solar storms will occur could protect countless lives and billions of dollars in infrastructure. And there's another more philosophical dimension to this story. For the first time, humanity is no longer simply a passive observer of the sun's behavior. We are becoming participants in a dialogue with our star, able to monitor its hidden rhythms and anticipate its actions. This marks a new era in our relationship with the cosmos, and it is only the beginning. Solar Orbiter's discoveries will feed into a global network of missions, Parker Solar Probe, SOHO, ground-based observatories, building a comprehensive 360-degree understanding of our star. We are assembling the first true space weather intelligence system, one that can warn us of coming storms and, perhaps one day, help us shield our planet from their effects. But beyond the practical benefits lies a deeper truth. By seeing the sun's poles, by uncovering their secrets, we are not just protecting our technology, we are expanding our understanding of the forces that shape life itself. Because in the end, everything we are, every breath, every heartbeat, owes its existence to the dynamic, living engine at the heart of our solar system. And now, at last, we are beginning to see it whole.